further ado, let's do like the two single problems that I ask of you. So number 7, describe the energy changes that take place when a small spring-driven toy vehicle is wound up and then released. And I told you like before here that you have to start somewhere, and let's start with the person winding this. Okay, let me mute everyone here because there we go. So let's start with the person winding this toy. So anyone wants to share their answer? Quick. So number 7. Yes, Madhav.
I had you start off with chemical energy, then
Excellent.
you transition into kinetic energy via
Okay.
human muscle.
Okay, I don't want you to be like too too detailed too, right? Okay, so this is you, right? Like chemical energy,
Mhm.
all right? And just go to the toy right away, okay?
Oh, okay. So you have your motion turning into elastic potential energy
Yeah.
with the spring
Yeah.
stretching out, and then as you let it go, it regains its original shape and turns into kinetic energy for the car.
Very good. Excellent. So if I share here, this is what I'm looking for. That's very good. Give us a second here. Yeah. Uh, so that's correct. So you have like chemical energy. So you are exerting a force. You used up like chemical energy in your body here, and this gets transformed into elastic potential energy, right? As you wind the toy, wind the toy here, and of course, as you release it, it goes back to kinetic. What goes back? It's kinetic energy of the toy, right? Okay. So as a spring regains its shape, right? Grain shape. Very good. Excellent. Okay, the next one. Okay, so some people were. Okay, next one. So billiard ball transfer energy to cue balls to set it in motion in terms of energy. Describe what happened when the ball bounces straight back off the side cushion. So we're going to start with the ball already in motion here. So at some point we have to start somewhere. So anyone would like to share their answer for number 8? Yes, Max.
I wrote, so you first have
Speak louder a little bit or closer to the
s-
mic.
okay, so I wrote that you first have the kinetic energy of the ball,
Yeah,
and then when it bounces off the wall does negative work on the ball, and so the ball will have kinetic energy in the opposite direction of motion.
okay. It's a bit hard like to hear you. I don't know if your mic or the volume is very low. Uh, but it's a side cushion here, right? It's a little side cushion. So this is your ball here. That well, I don't know because I don't see myself here. Let me see here. No.
Oh, okay, yeah. I see.
Uh, so you have the ball here. You have the cushion. So what happens here when the ball hits the cushion? What happens to the cushion?
There will be like some sort of like elastic potential energy
Yes,
as
that's
well.
correct.
Okay.
That's correct. So so what happens here is that you have kinetic energy of the ball. Now it's transferred into elastic potential energy. All right, of the cushion here. So as the ball compresses the cushion. All right. And then what happens next? So of course, like the cushion does work on the ball, slowing it down, The kinetic energy does, the ball does work, of course, on the cushion, crushing it, right? Okay, and then what
So-
happens after?
So the cushion regains its original shape and releases its elastic potential energy, and the ball has kinetic energy.
Very good. So now let's go back to, there we go. So as cushion regains its original shape. Whoops, regain its original shape. Its original shape. Whoa. All right, good. Excellent. All right, so kinetic energy here. Yes, Madhav, kinetic energy comes in, compresses the cushion, which is like an elastic, store elastic potential energy, regains, and then transfer back into the ball. Yes.
Would you ever see a situation where kinetic energy turns into other kinetic energy, or is there always kinetic energy to potential and then back to kinetic?
No. You like if you have like two billiard balls, like you have a static billiard balls and one that is moving. So there's kinetic energy transfer from one ball to the other, right? To the kinetic energy of the other one. All right, especially if the ball are very, very, very hard. So there's hardly any like spring-like behavior. So it'll be a kinetic energy of the ball transferred to kinetic energy of the other ball. Remember like those, what the Newton pendulum is? They have like 4 or 5 like hanging and then boom,
Yeah.
and transfer. So it transfer kinetic energy from one to the other. Actually, transfer also momentum, but something you're going to learn next year. Okay, good. All right. So as I said here, I want to talk about thermal energy here because I've got like quite a few things to say about this, and I feel that tomorrow I don't think I'll have enough time to compress all this. All right. So here is a glass of water. At the moment, the glass of water is at rest. So if I ask you, like, how much kinetic energy does this water have right now? What would you answer? How much kinetic energy does this body of water has? Max?
0.
0, because it doesn't
Move.
because it doesn't move. Very good. Okay, so as a matter of fact, here, like this body of water here has plenty of kinetic energy. There's 2 types of kinetic energy here, all right? There's the kinetic energy of the body as a whole. So as a whole, this water, this glass, right, it doesn't move. It doesn't have kinetic energy as a whole. However, this kind of misleading here because water and the glass is made up of what? Come on, grade 9. Matter is made. No, raise your hand. Not raise your hand. I don't want like everyone else like to. All right, so I see Max here. Anyone else? Okay, Max.
Water is made out of like H2O, and
Yeah, okay.
sand is made out of. Sorry, glass is made out of sand.
Yeah, okay, all right. But in general here, matter is made up of. Raise your hand.
Tiny particles.
Aditya, you don't.
Oh.
Aditya.
Particles.
Yeah, tiny particles, right? There are 2 types of tiny particles. What are they? Raise your hand. I don't know why I don't see like raising hand here. I guess I have to. Madhav?
Molecules and atoms?
That's correct. Molecules and atoms. So what you've learned in grade 9, you've learned the following. Let me see here if I don't know where. Anyway. So you've learned in grade 9 that matter is made up of tiny particles, either atoms or molecules. But this is very important here. Those tiny particles, there are always in. Raise your hand. Always in. Yes, Leo?
Motion.
In motion. Something that may not have been stressed in grade 9 and grade 10 is that this motion is random. Very important. This motion is random. All right? So if I go back to my glass of water here, the The water here, particle as a whole, of course, it doesn't have kinetic energy. But water is made up of tiny, tiny particle, water molecules, and these are constantly in motion. And it's random. So some water molecules are going this way, some water molecules are going that way, some other molecule slides this way, right? It's completely random, but they're always in motion. So if we, so each water molecule here, by virtue of the fact they have speed, they have kinetic energy. Mind you, the kinetic energy that a water molecule would have, or a tiny particle such atom or molecule, would be super tiny because the mass is immensely tiny, right? So kinetic energy is proportional to mass. So if the mass is really, really small, kinetic energy is very small. So the kinetic energy of any one of these water molecules here is super, super small. However, you have millions and millions and millions and millions and millions of water molecules here, right? You have moles and tiny, enormous amount of moles here in this glass of water here. So if you take all those kinetic energy that are from each molecule here, very, very small, and you start adding them up, well, you're going to get like a very big number, right? And so this number that you get when you add up the kinetic energy of all the tiny particles making up an object, this is called internal kinetic energy. I don't like the term, so I'm never going to use internal kinetic energy. What I prefer to use is two terms. We call this relative kinetic energy, because it's relative to the body of water. So the water here doesn't move, right? But relative to this, the water molecules are moving. The term I prefer, though, is microscopic kinetic energy. So microscopic, micro, all right? So any object here, any object that you touch, all right, or it's called macroscopic, all right? So M-A-C-R-O, so it's big, right? So all macroscopic objects are made up of microscopic particles, right? So molecules or atoms, okay? So this body of water here, the total kinetic energy of this is made of two parts. The kinetic energy of the body as a whole, which in this case here is 0, plus the kinetic energy of all the tiny particles making up this body of water. Now, when this water moves, it has kinetic energy as a whole, plus the kinetic energy of the motion of the molecule inside, all right? So even though like a body as a whole may not move, it does possess kinetic energy by virtue of the fact it's made up of tiny particles, and those tiny particles are in motion all the time. And given I understand that the kinetic energy of one molecule is very, very small, but since in microscopic object you have millions and millions and millions and millions of particles, if you add up like a very small quantity, you end up like with the big one. So the same like Lake Ontario, right? Can you empty Lake Ontario with a spoon? Yeah, you can empty Lake Ontario with a spoon. It's going to take like quite a bit, probably like longer than your whole life, but you can. All right. Okay, so let's go back to share the screen here. All right. Okay, so thermal energy. All right, so thermal energy. All right, so we're gonna have like consider a body of water. All right, so here it's going to be the glass. Okay, so glass. All right, and we're going to have water right here. So let's put it like blue. Of course, water is transparent. And we're going to put like a little water molecule here. So as he said here, this is made up of H2O. So water molecules right here. All right, so water molecule. And this is always in motion, right? So, and don't forget here that this motion is random, right? So always in motion, right? Always in motion. Of course, this is not to scale. So, so each, whoops. So each water molecule has kinetic energy. Okay. And if you add the kinetic energy of each molecule in the water, body of water, okay, you obtain the relative or microscopic kinetic energy. Kinetic energy. All right. So, so basically, the microscopic kinetic energy is equal to this. All right. So it's a summation over all the kinetic energy of each molecule here. So let's call this here like Ki. All right, so Ki. So this is what a microscopic kinetic energy is. This is also called relative, but I prefer like microscopic kinetic energy. Actually, I put it like this. This is how I put it. All right. So remember here, like this means summation. So summation of all the kinetic energy here. All right, of all this. So the total kinetic energy of an object, so total kinetic energy of a macroscopic object is equal to the kinetic energy of object as a whole plus the microscopic kinetic energy. All right. So the total energy of, so total energy here of kinetic energy, microscopic object, like this, like anything this, right? this is the kinetic energy of the whole object as a whole, right, as it moves. Remember FBD, I asked you like to draw like a big fat dot. Well, this is what it represents. A big fat dot is the whole body as a whole, all right? Plus, of course, the microscopic kinetic energy inside. Okay, so far so good? Okay. Now, so temperature. What can you tell me about, so if I have, let's say I have 2 glasses of water. I know you cannot see this here, but let me see here. All right. If you have like, if I had 2 glasses of water right here, and one would be hotter than the other one, what does that mean in terms of, if you had a very powerful microscope here, what would you see different in the hotter water body compared to the low water body? Yeah, Leo?
The water molecules will be moving faster.
That's correct. So the water molecule in the hotter body would be moving faster. That's exactly correct. And the water molecule is still moving in a random direction. It's very important that you understand this. It's random, all right? So the temperature so let's see, T here, is a measure of the average kinetic energy. Average kinetic energy per molecule, per tiny particles, per particles. All right, that's what temperature is. Temperature is related to the average kinetic energy per particle. So if we consider, so what it means here, it means this. It means that temperature is proportional to this. So if you take the microscopic kinetic energy of a microscopic object, right? And you divide by n, where n is the number of tiny particles, right? So this is the average here, right? This is the average kinetic energy per particle. All right, so where n is the number of particles. The particle in the microscopic object. Okay. So once again here, temperature is proportional to it's a measure of how much kinetic energy there is per particle. Now in this, this glass of water here, there are water molecules going faster and some molecules are going slower, right? Some are going faster, some are going slower. But if you take like on average, the kinetic energy of all these, right, there'll be an average. And this average here corresponds to, is related to temperature of this body of water. So at the moment here, the temperature of this might be 20 Celsius or so. And it gives you a measure of how much average kinetic energy those water particles have. A hotter body, on average, a kinetic energy will be greater. Since the mass of all the particles here in the pure substance are the same, so that means that in a hotter body, because kinetic energy is mv squared over 2, so it's not only v, it's only the mass. But for a pure substance where the mass of all the tiny particles are the same, So a hotter body means that the particle will be moving more. All right. Okay, you good for that? All right. Good. Well, that's it for today. I told you it'll be like very short. Not everyone is here. Who's missing here? Quite a few. 37. Whoa, I don't know where the rest of Squad 43 should be like 6 more. Yeah, thank you, Aditya. Okay, good. So so we'll continue on this tomorrow. You have like some homework here. I just put it on your website. Just read this, talk about temperature, talk about the unit of temperature, how it's, they talk also about thermal conductivity and all this. All right, so do the problems today on this. We'll take it up tomorrow, and then we'll continue on thermal energy. All right, guys? Okay, so any questions? Okay, so I'll see you tomorrow, guys. Bye-bye. I'll leave this on like just for 1 minute or so. Some people are not quite done.